Hello everyone, welcome and thank you for joining me in this session where I'm going to explore how we can use Elixir to simplify the implementation of our software systems. Now, when I say the term software system, I'm referring to a particular type of software, for example, such as web servers or say databases, message queues, and similar kind of programs. And what's common for all these examples of programs are a couple of properties. So first and foremost, these are the programs which when you start in production, they have to be running constantly, continuously, preferably with no downtime at all for a long period of time, like say many years or maybe even many decades in some extreme examples. And while they're running, at any point in time, they have to perform a bunch of different tasks. A bunch of different activities are constantly happening in the system, such as, say, handling different incoming requests, but also beyond the request to response cycle, running some background jobs, like, say, communicating with external third-party services, running some periodical jobs like cleanups, managing some kind of in-memory states, such as caches, having some sort of queues to communicate between different parts of the system, managing load, so controlling the load, like applying back pressure or rate limiting, and so on and so forth. So a bunch of things are happening, a bunch of activities are happening in the system. And what's really interesting is that these activities are like mostly mutually loosely dependent. Many of them are like completely mutually independent. And so the system operates in sort of shades of gray of availability of success, right? It's not binary. It's not like it either works or it doesn't. So like, for example, if a single request fails, that doesn't mean that the entire system has to fail, and we can still provide most of our service to most of our users. And this is a very interesting property of software systems, but not of all programs, of course. Now, typically how we are approaching these challenges, these particularities of software systems is through a plethora of different approaches at different levels. So like at the very lowest level, you might start using non-blocking input-output to separate latencies of different activities like different requests. Then you might run multiple copies of a web server locally and install some sort of a load balancer / reverse proxy in front of those. So you may run a couple of OS threads or a couple of OS processes for that. Then you might split your system into a couple of OS processes, a couple of microservices, for example, to improve your fault tolerance. Inevitably, when you go down that path, you're going to need to reach for some third-party components, such as a reverse proxy / load balancer, for example, Nginx. You might also need to have some sort of a in-memory KV as a product, so say Redis, some sort of a message queue. And then, of course, you will definitely need to use some kind of a service manager, such as systemd at the very least, to organize all these separate OS processes at the OS level. And of course, if you want to get fancy, you can reach for Kubernetes, for example. Now, these are, in my personal view, like very popular, standard approaches, one could say, these days, and have been for many years, in fact, in our industry. And while these approaches most certainly work, I personally feel that in many cases, we end up throwing this huge and complex machinery to solve relatively simple to maybe moderately complex problems. And in the process, we are actually introducing a large amount of technical complexity into our implementation. And what I want to show you today is that using languages such as Elixir, you can actually reduce significantly, and in some cases completely eliminate this technical complexity, and you can get the same benefits and even better and bigger benefits, and at the same time have a much simpler implementation. Now, Elixir is a programming language from the Beam family of languages. So there are a couple of others I have listed here, and many more which I haven't listed here. And what's really common for all these languages is that they use the same runtime, which is called Beam, and this is the Erlang virtual machine. And essentially all the benefits that I'm going to mention here today come from Beam, right? So I'm going to talk exclusively about Elixir, but really everything I say apply to all Beam languages, past, present, and future. Now, an interesting thing about Beam as a runtime is the fact that it gives us like the services or features that you typically get only at the operating system level. We get them directly at the runtime and therefore directly in our language. So the story goes like this. Like say you write a program in, for example, Elixir, and you start your program somehow. What happens is a single operating system process is started, and this is the instance of Beam where the program is running. And inside that single OS process, you can run and manage a large number of independent, lightweight, small programs, which are called processes. So try to memorize this word process. Process means a small independent program inside Beam, inside that single OS process. So process is not an OS process, okay? So one OS process, this is the Beam instance, and a large number of these small little yellow boxes, these processes, these independent programs. And when I say large, I mean like hundreds of thousands or even millions. Like I think the maximum limit is somewhere around 100 millions per single Beam instance. So you can really run a large number of these programs inside a single OS process. And those are like regular programs, sequential programs written in, say, Elixir, Erlang, or whichever language you choose. And these programs are completely isolated from each other, so they share no memory. They are separately garbage collected. They can only communicate by sending themselves messages, which is also known as message-based concurrency. They fail separately, so like if a single program fails, single process fails, all others are still up and running, providing most of the service. And then finally, Beam spreads the execution of these processes across available CPU cores. So immediately out of the box, you get multi-core capabilities. So that's essentially all I have to say. That was a very quick intro about Elixir and Beam in general. I understand that it's very vague, leaves a lot of questions open. So I'm going to do a small self-promotion, self-plug, and forward you to my own talk from about a year ago at GOTO Chicago called The Soul of Erlang and Elixir, which is essentially 40 minutes demo-driven exploration of Beam concurrency. And so if you want to learn more about it, you may want to take a look at that talk. It's available on YouTube. But anyway, like the big point of Beam, again, is that we get like sort of an embedded out-of-the-box support for like microservices directly at our runtime, directly in our language. And we don't have to fall back to the operating system level to get those properties, like run a bunch of independent programs. And therefore, we can solve a lot of problems directly in our language. And we can have like a monolithical organization of our code. We can literally have a monolith, a single project written in a single language, but internally it's still spread across a large number of independent programs. So like essentially micro, nano, pico services, if you will. And I'm going to show you this in practice. I'm going to do a small case study of a very simple, very small system, but still a system which runs in production, which is out there on the internet, accessed globally by millions of people worldwide. And this system is called the Erlangelist. Now, the Erlangelist is my own blog post hosted at the Erlangelist blog site, hosted at theerlangelist.com. And it's written exclusively in Elixir. So organized as a monolith, it's a single project written in Elixir, and it's open sourced. So essentially, it's very easy to have run your own copy of the Erlangelist locally. There are like 4 steps, only 3 are listed here, but step number 0 is, of course, installing prerequisites, basically Erlang, Elixir, and Node.js. The latter is needed only to deal with assets, like to bundle assets such as JavaScripts and style sheets. And once you have the prerequisites installed, you clone the repo, fetch the dependencies, invoke a single command, and you are running the entire Erlangelist. So like everything that is running in production is running also locally on your machine. There is nothing happening on production that isn't running locally on your machine. 100% of the system is running locally. So it's like super simple to get started, and the Erlangelist is really supported by nothing else on the side, no third-party products or something like that. Now, this may not seem like much for a simple blog site, because the Erlangelist is really, in terms of complexity, as simple as it gets. It's basically a statical content server. This content changes like very, very infrequently, basically when I write a new post, which happens like once a year or so. But still, behind the scenes, things are happening which are not immediately obvious. And I'm going to show you some of the things that are happening. I'm going to show you the process structure powering these different features. But one big point I want to say here is that, like, I frequently hear people speaking terms such as web app or a web page or say a web server. And to me, what we are building is more than that. So like as a backend developer, I look at this as a system, you know, a bunch of activities happening. It's way more than just a request responder. I mean, to the end user, of course, it is an app or it is a page, but to us, the backend developers, it is a system. And I want to emphasize this because, again, a bunch of stuff is happening in a system, even such a simple system as the Erlang list. So yeah, let's take a look at some of the features and the process structure powering different features. And I'm going to start with like the most obvious one. And this is serving requests, right? This is basically what the system has been built for. So like you visit www.theerlangelist.com and you get served some blog post. Now the process structure powering this particular part of the system looks, simplified version looks as follows. So in the system, so again, the blue box is the system. It's like the Beam instance, that single OS process, and little yellow boxes are small programs within that single OS process, these processes. Right, and so among a bunch of these processes, we have two. One listens on port X for HTTP traffic, another one on port Y for HTTPS traffic. And once a request arrives, once a request arrives, each of these processes will spawn separate processes to handle those requests. So each request is handled in its own separate, temporary, short-living, one-off process. So like if we have a million requests at the same time, we're going to have a million of these processes at the same time. And if we have 0 people around, then we're going to have 0 of these things. So they're like very dynamic in their nature. And again, you know, these processes are super lightweight in terms of startup time and memory overhead. So you can really run a large amount of them simultaneously. So this process structure, first and foremost, it's not something that I wrote myself. It's given to me courtesy of the library that I'm using, or in this case, a framework. It's called Phoenix Web Framework, which is like the GOTO solution in Elixir to write web-facing systems. Basically, the library just organizes this process structure, and pretty much any web library that you're using in the Beam ecosystem is going to do a similar take with respect to process organization. So I didn't have to invest any work into this myself. You know, I'm just using library as advertised. But the question is, why do we have such process structure? And so there are a couple of benefits that we get. The most obvious one is a multi-core capability, right? Because by splitting the total workload across a large number of small independent programs, I provide the opportunity to Beam to spread the execution of these processes across available CPU cores. So I get potential for parallelism and I get vertical scalability. Like if the system is maxing out on the current machine, so for example, the Erlang is running on like some super weak, super small box, which I'm paying for like about $5 a month or something like that. And if it's maxing out on that machine, I can put it on a bigger box with more CPU cores, and it just takes advantage of all this extra hardware that it is given. Right, so I get vertical scalability with such process organization. Furthermore, I get fault tolerance. I get separation of failures. Like if something goes wrong when handling a single request, say like a division by 0, square root of -1 or something like that, that process would crash due to an unhandled exception, but everything else is still running and I'm providing most of the service. So I still have large availability or close to max availability at any point in time. And then finally, this process organization allows me to separate latencies of different activities in the system. So again, if like a single handler runs for a long time due to, say, a bug, suboptimal implementation, or maybe some external reasons, like it's contacting external service, which is slow, everything else is unaffected. Even on a single core machine with just a single thread running, even then, due to how Beam does scheduling of these processes with very frequent context switching, even then a long-running process will not significantly affect duration, latencies, or the execution time of other processes in the system. And so in summary, out of the box, courtesy of using Phoenix Web Framework, this library, not a product, but a library, I get multi-core capability, vertical scalability, separation of failures, separation of latencies. I also get typical features of any web server, such as, say, support for compression, serving statical files directly from the disk, and so on and so forth. And I really didn't have to invest pretty much any work into that. And essentially, I don't need to run multiple copies of the server locally, and I don't need a load balancer in front of those copies. And what this means is that the typical component, such as Nginx, is not needed. And in production, the Erlang list is not using Nginx. It listens directly for the incoming traffic on ports 80 and 443. And so that's one typical complex technical component out of the window, removed from the table, and this simplifies my implementation, because I don't need to worry about that extra third-party product and deal with like this Nginx configuration with those ini files and whatnot. Okay, so that was about serving requests. Now, as I said, there are a bunch of other things happening in the Erlang list beyond just plain request responses. So this is the property that you typically want to have, or the feature that you want to have in any kind of a production system, no matter how small or big. You want to gather some statistics about the system usage, right? And so for the Erlang list, I kept it to a bare minimum, super simple and stupid. Essentially, I'm collecting the count of the read count per article per day for the past 7 days, and that's basically, I want it just for vanity purposes. So like when I publish a new post, I want to see how frequently is it accessed, especially compared to previously published posts. Now, normally for this, you would want to have some sort of a database, like say PostgreSQL or something, because you want to persist this data so it can outlive restarts. However, in the Erlang list, I actually rolled my own database, not a general purpose one, but very lightweight, specialized one for this particular scenario. Now, this seems like somewhat unorthodox, but it made sense for me because my use case here is super simple. This data is what I like to call nice to have data. So normally I want to have it, but if I happen to lose it occasionally, I won't really shed a tear. And so I can make different kinds of trade-offs, right? And I wrote like this lightweight built-in database in Elixir, again, very specialized, not a general purpose one. And with that, this complexity of dealing with a third-party database, and that's like a huge amount of complexity, which involves installing the database, setting up some roles, dealing with migrations, like creating database structure, and then finally dealing with impedance mismatch, data going from Elixir to the database and then back. All this stuff flies out of the window, and again, much simpler technical implementation, which is not as fancy as PostgreSQL, but it's perfectly sufficient for this particular use case. And just in case you wonder, I also had pretty much any production, I had such cases where I had to deal with this, what I like to call, again, nice to have data, where just doing something on my own in like say 100 or max 200 lines of code was actually much simpler than having to deal with external database. So anyway, process-wise, here's how it looks like. So among all these processes, we have a singleton process, a well-named process, well-addressable process. It's called stats collector here. And so we have these request handlers, which are handling incoming web requests. And when a request handler serves the article, it's going to send a message to the stats collector, like article full read, article bar read, article buzz read. And stats collector is going to keep an in-memory state, a mapping of the article ID to the read count. And so it's just going to bump the corresponding counter. Now, a big thing here is that stats collector can work in concurrent environment. It can serve multiple simultaneous clients. And that happens because it's a single process, and process is a sequential program. So it handles one message at a time, and therefore it's a point of synchronization. It's a point of consistency. And so we don't get typical error, typical multi-threading or typical concurrency problems such as race conditions, live locks, deadlocks, and so on and so forth. So it works perfectly fine in multi-threaded or concurrent environment, and it can handle multiple simultaneous clients. Now, the stats collector is, as I said, it aggregates data in memory, but when it comes to storing data, it actually will occasionally fire off a separate one-off temporary process, which is going to flush this data to disk. So we have this disk writer process. It's just given this data, and it just stores it to disk. Now, this separation is done again due to separation of failures and latencies. So by doing the writing to disk in a separate process, we ensure that when something goes wrong, and writing to disk can go wrong, like say if I don't have permissions or maybe the disk is full, the stats collector will still live, and it will still keep this data in memory, and it will aggregate further data. And then in some future iteration, when the circumstances allow it, some future disk writer instance will succeed. right? And so we have separation of failures, and we have like a lightweight self-healing property. Likewise, we get separation of latencies. So like if the disk operation becomes slow for whichever reasons, task collector is independent process, and so it can still keep aggregating this data. And in the next iteration, no matter how slow writing to disk is, it's going to store this data to disk. So we separate disk-based operation from in-memory operation. We separate their latencies and their failures. Now, another thing happening here. So like I'm storing this data into one file per each day, and I want to only keep the files for the last 7 days, and so I need to do some periodical cleanup. And this is also an example of something that I've needed in 100% of the systems I have ever worked in, no matter how small or big. There's always some need to do some periodical jobs, like say cleanup, or archiving and whatnot, maybe periodically access or poll some external service. Typically with other technologies, non-Beam technologies or languages, you have to fall back to the operating system level. So like you're gonna do a cron job or maybe a systemd timer or something like that. But in Beam, running a periodical job is as simple as starting the separate program which runs something periodically. Like in the naive implementation, it could be literally, such program could be something along the lines of while true, sleep X, do something, go back, right? The real implementation is a bit more involved, at least the way I do it, and so I want to show you this because this is the arguably the simplest, smallest example of thinking concurrently in Beam, of how granular, how fine-grained we get with these Beam processes. This is like turbocharged microservices, if you will, right? And so the essential idea is that we have two processes powering a single periodical activity. They always come in pairs. Like if you want to run 100 periodical jobs, you're going to have 100 pairs, 200 of these small processes. So one process is a scheduler. It ticks regularly every X in the desired interval. And so every X, it fires off, it starts this temporary one-off process to actually perform the task, to do the job. Again, we do this to separate failures and latencies. Like if this job fails, crashes for whichever error, the scheduler still keeps ticking unaffected, and in the next iteration it starts the new instance, which maybe succeeds, maybe doesn't, but sooner or later when the circumstances allow it, it will succeed. But the point is that we separate failure of the job itself from the job of ticking, of regularly doing something. Likewise, we separate latencies. So like imagine that this job is taking much longer than the interval. In the next iteration, the scheduler ticks, and now it can make a decision. You can make this decision on a case-by-case basis. Like you can decide to terminate the previous instance and start a new one. You can decide to start the new one side by side to the previous one. You can decide to run at most X and then start terminating the oldest ones. You can decide to do nothing and wait a couple of cycles more and then see what you're going to do. So you have a bunch of options at your disposal. It's actually way more flexible than your typical cron job or timer. And at the same time, the code is like really super simple and declarative. So this is how it looks like. Again, I'm using a library which does this. So instead of using a product such as, say, cron job, I have this as a library, just like you have JSON parser, for example. And it's still like a super declarative. So I basically say every minute invoke this function, and then I have a couple of different options how I can control this thing, and otherwise I can even have an imperative interface to be more flexible in how I'm executing this job. So, but the point is, it's like super declarative. I would say pretty easy to read, even if you don't understand Elixir, and at the same time technically much simpler and way more flexible than your typical opaque third-party components. Okay. One other thing I want to show you, because everything is now running inside the same monolith, inside the same project, it's actually testable, right? So I have tests that verify that I'm periodically cleaning up all stats, right? So this is a standard AAA test, arrange act assert. So in the arrange phase, I'm bringing the system into the desired state. Basically, I'm accessing the article 8 days ago, 7 days ago, 6 days ago, and then I send an impulse to the periodical scheduler. So in the test environment, it's not really ticking automatically. I have to manually send it an impulse. So I send it an impulse, and then I just verify that now that I access usage stats, I only get the stats for the article 6 days ago. So the ones from 7 and 8 days ago that were accessed 7 and 8 days ago respectively have been purged, right? And so I can actually test this. With cron job, you typically don't really test those things. You can test like that some function is actually doing what it's supposed to do, but you don't have tests like, is this job actually executing periodically? I had similar thing in a production system where we had like a periodical job executed at fixed schedule at like midnight, say UTC time. And we had a test that verifies that like at midnight UTC, literally we have this particular activity executed, and we then assert on the expected state of the system. So this gives me much more confidence, right? So again, it's way more testable than when reaching out for third-party products. Okay, the final thing I want to show you is how I'm serving HTTPS traffic, right? So Erlangelist basically, like I think any good system these days, serves traffic through HTTPS. I think that like from the standpoint of security and privacy concerns, this is really a good practice and should not be an option. Now, to serve HTTPS, you need to have a valid certificate accepted by browsers. And there are a couple of different options, many options how you can obtain the certificate. I opted for like a very popular one today called Let's Encrypt. And what's nice about Let's Encrypt is that it costs zero money, which is always a good thing. And then also that it can be automated, right? So instead of having a human obtaining a certificate, you can actually have a machine, a program doing it, right? And it looks roughly like this. So we have conversation, a dialogue between two systems. On the left, it's our system, like the Erlangelist, and on the right, it's a certificate authority, a CA, a system which is somehow officially recognized and authorized to issue valid certificates. And so our system initiates the conversation. It asks the CA server, like, can you please give me the certificate for the domain theerlangelist.com? And the CA server responds, sure, you can get it, but you need to prove that you actually are the owner of the theerlangelist.com. And so what we're going to do is following. I'm going to send you these random bytes now, and then I'm going to make a request to theerlangelist.com/somepath, and you need to serve those same bytes. And if you're able to do this, then you effectively prove that you are the Erlangelist and you can get your certificate. So the actual story is way more involved, but I hope that you get the gist of it. And so this conversation, the protocol of this conversation is called ACME, ACME, Automated Certificate Management Environment. And this, in my view, is also an activity of the system. You know, it's a program that has to be executed during the very first boot, and then occasionally before the certificate expires for renewal. And for me, it makes most sense to actually run it as a part of the same programming in the same place where the rest of the activities are running. Which is typically not the case otherwise. Like when you read the options for Let's Encrypt, most of the options are actually going to recommend to run some external program on the side, like say most typical or most popular option is a thing called certbot. So you need to run this certbot thing, and most often the promoted version will also ask you to have Nginx. Like you can do it without Nginx or reverse proxies, but that's like the most advertised option, at least in my impression. So if I wanted to do this with the recommended way, I would have to install this certbot thing, which brings in Python, and then I would have to run Nginx in front, and this again adds a lot of complexity. So in the Erlangelist, it's done a little bit differently. I'm using a third-party library, which incidentally I wrote myself. It's called Cite Encrypt. And I'm running this certification directly in the same system. So a simplified version is that we have this process called certifier. It's in fact a process structure, but either way, the point is that like when the system boots for the very first time, the certifier will initiate this conversation with Let's Encrypt. And in the middle of this conversation, Let's Encrypt will contact this HTTP server here, which is like the web server I've shown you before, and then we're going to respond. So everything is integrated in the same monolith, in the same OS process. And in fact, due to this structure, I don't even have to store anything to the disk temporarily, which otherwise typically happens with certbot and other tools. So it's very nicely integrated. Another interesting benefit of this approach is that I can also run a local ACME server, so like sort of a shim, a mock of Let's Encrypt. This is also supported by or powered by the library. So as a writer of the Erlangelist, I didn't really have to invent this wheel myself. So in development and test mode, I'm running this local ECME server, and the system, the certifier, uses that local ECME server instead of the real one, and therefore I can have the system, the Erlangelis, certifying itself locally. And this is important because it allows me to reduce the gap, the differences between the production and local version. So when I told you that when you start the Erlangelis locally, you're running everything, you are literally running everything. Even this ECME certification takes place. Of course, it has to be through a local server because you don't have a publicly exposed domain. So let me show you this through a simple demo. I'm gonna walk you a little bit through some things of the Erlangelis. So this is the Erlangelis project. I'm gonna invoke first Erlangelis clean helper task, which cleans everything like the previously existing certificates and whatnot. And so this is like I'm starting the Erlangelis for the very first time on this machine. And so I invoke this magical command, and within a matter of like a second, the site certified itself. So let me just show you this. So I started the site. It first generated a temporary self-signed certificate. This is just so we can start listening. So this is still not ECME. So then I start the endpoint. Endpoint in Phoenix lingo means server. So I start HTTP and HTTPS web-facing part of my system. Then I start local ECME server, all within the same OS process, right? So I can run multiple servers in the same OS process. And then we are creating a new certificate authority account. And then a little bit below, we are ordering new certificate, and it has been obtained. And now the Erlangelis is serving, it's self-certified using the ECME protocol, and it's serving, so you can see here on port 2443, it's serving HTTPS. Of course, the browser complains because this is still a self-signed certificate. It's not authorized, but the point is that I actually ran this flow as I'm running it in production, and we can see this certificate here, the erlangelis.com. Now, let me just show you briefly another thing. So again, I spoke about a lot of activities, so let's visualize this. So there is a tool called Observer, which I can start this thing, although GUI is also implemented in plain, in this case, Erlang. It's from Erlang Standard Library. And this is a so-called supervision tree of, it doesn't even fit on the entire screen, of the Erlangelis, of the local Erlangelis. And basically, each box is its own separate process, organized in a sort of tree-like hierarchy of parents and children. And I like to call this like an embedded system D, because it gives you pretty much the same kind of features, like the ability to organize how the system is starting, in which order is it starting, how things are interconnected, like if something stops, then stop that other thing. So for example, if blog endpoint stops, which is again the web-facing part of the system, then we're also going to stop these two processes, which are the certifier and the local ECME server. And so it gives me similar features, but again, embedded in my language and interfaced through with the same language as the rest of the system. And it's, again, much more flexible. So for example, this part of the tree here, this is the local ECME server, which is only started on local development and tests. So like very, very flexible. And I don't need to fall back to the operating system level to get such properties. And maybe just as another small point, I have this thing here called dashboard. So dashboard is yet another web server running, which I didn't even mention. It's kind of like a very lightweight embedded graphite. So a site which is not exposed externally, it's only exposed on an internal port, which gives me some sort of metrics dashboards, so I can get some insight about the system usage and the state. Okay, so anyway, that was that. So again, you know, the big point is that the differences between production and development are reduced, and this holds not only for development but also for tests. So like, let me show you some tests here. This module here is where I'm testing the blog, the web-facing part. So I'm testing, for example, whether a root page shows the most recent article, and so on and so forth. And so then I have a couple of interesting tests. So for example, I'm verifying that HTTP requests are redirected to HTTPS. Normally, if you configure this in Nginx, then this is not going to be tested. You kind of configure it, test it in production first time, and then you're hoping that it's not going to be broken. But here I actually have tests which can verify this kind of behavior. So again, the the differences between production and dev/tests are pretty much non-existent, other than the fact that I'm using local Acme server and not the real let'sencrypt.org. Therefore, I can also test that dearlangelis.com is redirected to www. And then another interesting thing, I can test the certification process itself. So this is powered, just 3 functions and powered by the cite encrypt library. So this function here is going to clean restart the endpoint. What this means is it's going to stop the endpoint, the server, clean all existing certificates, restart the endpoint, and because this is now a first boot, the endpoint is going to self-certificate using Acme. And this function will return only when and if this succeeds. And so here now I can obtain the certificate of the endpoint, and let's just go into this function. It's from the library, but let's take a look so I can demonstrate. This certificate is obtained not by looking into the disk or something like that. We actually establish the SSL connection to our server, and we fetch the certificate of the peer. And so it's really demonstrating that dearlangelist is serving using this particular certificate. And now I can assert something about the certificate, such as whether it has the expected domains that I've ordered. And what this gives me is more confidence, let's go to the code where certification is configured. So again, this is like very, very declarative, but still this is not ini, this is not YAML, this is code which is invoked during runtime. It looks declarative, but it's still a programmable API, and I can invoke some functions, and I can have some ifs and else's, fetch some data from the database, like fetch some metadata here from the database and whatnot, like super, super flexible, right? And so anyway, let's say that I make a mistake here. Let's say I have a syntax error. I added another comma here, and I save this thing, and immediately, like even in the editor, I get a compiler error. So unlike ini, YAML, and whatnot, if there is a syntax error here, this thing is not even going to make it to production, not even to the main branch. It's just going to fail during the CI build. The same holds if I make a semantical error. Like syntactically, it's correct, but let's say I have an extra e here, so it's like the Erlangelist instead of the Erlangelist. Hopefully I vocalized this distinction properly. So yeah, syntactically this is correct, but when we run tests, let's just wait for them, and bam, our test is failing, right? So the test's certification is failing because the domains are not as expected. So, I get more confidence. I can test more things because everything is nicely integrated into that same monolith. Still organizes like microservices, except way more fragmented, way more granular or fine-grained than you would typically do with microservices. And then finally, this thing here simplifies my operation. This monolithical, uniform organization, just powered by Elixir. So let me just show you the Docker thing. So I run system in Docker. There is not much need for that, but I still want to have it Dockerized because this allows me in some cases to really iron out or eliminate pretty much all differences between production and development. So I don't do typical development in Docker, but occasionally I just want to try things out. Anyway, this is the Docker file for the system. It's a multi-stage or 2-stage Docker file. So stage number 1 is builder, where I'm just building the deliverable, which is so-called OTP release. And the key part here is the very last command. So before that, I start with Elixir, Alpine, Docker image, and then install a bunch of prerequisites like Node.js and whatnot. And essentially here I'm building the release. And so this is going to build a folder structure, which is going to contain the minimal Erlang runtime binaries, and it's going to contain Elixir binaries, my dependency binaries, my own binaries, bundled JavaScripts, style sheets, images, and whatnot. And so this thing is self-contained and standalone, and I can just take it and put it to another machine without needing to install anything there. It has to be the same operating system, though, and that's another reason why I like to use Docker. And so this is the release then. It starts from raw Alpine, and you can see how very lightweight it is. Here I'm copying over stuff the release built in the builder phase, and at the OS level, this is the only prerequisite I have. So I don't need to have Erlang, Elixir, and whatnot installed. Only ncurses, which is required by Erlang, and that's pretty much it. And so the operation is way, way simpler, and basically it boils down to mounting volumes for like certification database and some backup, which I want to have preserved even when I restart the Docker image. And then final thing, also related to operation, operation is now driven by programmatical API. So like if I want to do something like manage this certificate manually, typically they are renewed automatically, but let's say that I want to do something manually. What I can do is following. I have a helper script here, which will connect me to the dearlangelist.com and give me an IEX session. And what I get here is interactive Elixir session in the context of production. So now I'm running at the production at dearlangelist.com. And here what I can do is, for example, stuff such as cite encrypt force certify, and here I would provide something like Erlangelist web.blog.endpoint, and this would generate a new certificate manually and apply it to the site. Likewise, I also have cite encrypt.dry certify, which I can use to generate a certificate but not apply it to the site. And I can also use this thing to actually use a different kind of Acme server, like say staging Let's Encrypt. And so it's driven by code, by the interface are Elixir functions. It's super simple for me because there's nothing else for me to learn, no special technology. Basically, to work with the Erlangelist, all you need to learn is Elixir and the problem domain. So you can actually focus on problem domain much more easily. But if I wanted to provide some sort of a more user interface friendly or user-friendly interface for, say, a non-developer operator, like I can always do this on top of such programmatical API. I can provide like user interface, or I can provide a YAML-based interface and whatnot. This is always possible to build on top of this programmable API. But the reversal is either very, very hard to build, and it will require a lot of improvisations and hacks and whatnot. And in some cases, it's downright impossible. And so this is also another thing that I like. So anyway, to summarize, oops, there we are. To summarize, Elixir and basically Beam and Beam languages allow me to start super, super simple. As we have seen, like in some cases, I can start using nothing but a single language in a single monolith project running as a single OS process in production. More realistically, you're probably gonna have to reach for a proper database, and I will definitely use it when I want to properly persist some data, and that can take you very, very far. And of course, when you do have some more important needs, you can always step outside of that technology. You can always go for the more traditional approaches, reach for third-party products, like say Nginx, if you want some, if you care about, for example, performance or throughput, or maybe carve stuff into multiple microservices if you want to. So you can always do that, but you have much simpler options at your disposal. You can start lightweight and expand from that as you go along. And this will reduce the amount of technical complexity in your project. It will reduce the gap, the differences between production and local development, and make your system more testable, and therefore give you more confidence about your system. And these are all very, very important benefits. And this is why I'm personally a huge fan of Elixir and other Beam languages, which I have been using in production for the past 10 years now. So that's pretty much all that I had prepared for you. Thank you for tuning in. Thank you for your time and your attention. In case you have any questions, feel free to ask me. And otherwise, hope that this talk has motivated you to explore Elixir in more details. Thank you very much.